before we get started, be thinking about if you'd be interested in taking notes. I say the magic words to get you to look at your laptop.
Okay, folks, can you hear me okay?
Yes, a little bit louder would be lovely.
Okay, let's see. How about this?
Yep.
Okay, very good. Let's get started. Hi, everybody. Welcome to CCWG. I'm Reese Enghart, and my co-chair Eric Kinnear is in the room. This is a hybrid meeting, as you can already see. If you are in the room, please scan the QR code in the room or use the link from the meeting agenda. This session is being recorded, and the recording will be uploaded on YouTube. If you want to speak, please use the tooling to raise your hand. So if you're remote, please mute your audio and video unless it's your turn to speak, and please use headphones. If you're on site, please use the raise hand feature and then line up at the mic in the room. And please remember to state your full name before speaking. This is the IETF Notewell, and it's fairly early in the week, so I'm just going to go over a couple of reminders regarding IETF policies and processes that you agree to by participating in this session. The IETF has IPR disclosure rules. So, for example, that means that if you are aware that any IETF contribution is covered by patents or patent applications that you or your sponsor own or control, and they are not yet disclosed, you must disclose the fact or not participate in the discussion. And you must file the disclosure within days or weeks and not months. Also, regarding privacy, if you speak at the mic, you will appear in the public recordings, and please see the IETF privacy statement for more information. And there's a couple of resources linked out from these slides. You can get to these slides from the data tracker. We require respectful conduct from all of our participants or attendees. If you have any questions or concerns, please talk to us, chairs. For example, you can email us. And there's also an ombuds team to help you. So please make sure you read our code of conduct and anti-harassment procedures. They are important and they are central to making sure that we can do the best work possible in this space. All right, here's some links mainly for people looking at our slides on their devices. We've made a lot of progress since IETF 121. So we published our first RFC in this group, our new BCP 5033 BIS, just out last week as RFC 9743. We also adopted a draft, the rate limited senders or rate limit increase draft. And just after the previous meeting, we confirmed consensus on our GitHub usage on the mailing list. So just a quick reminder on how we use GitHub in this group. We have a GitHub organization linked out from this slide. The GitHub organization has at least our adopted drafts, and we invite participants to file issues and PRs in those repositories. And thank you to everybody who has already done so. As you suggest changes to a document, please share the motivation for those changes as well as any test results that you may have ready to share. And please let us know if you can help gather such test results or if you want somebody to help you gather test results. And in general, more data is always good. So this is our agenda for today. We already have a note taker. Thank you, Martin Duke. And we will have a couple of items on our agenda. First, we have an update about tools for testing, including a hackathon update. Huge thank you and shout out to Mohit and his students. They're going to recap some progress that they made this hackathon and in general talk about test tooling for congestion control. And we really value test results for our proposals and suggested changes. So we're very grateful for this talk. And then we are going to talk about our adopted proposals first, and then talk about other proposals that we have been discussing in CCWG, and we look forward to continuing those discussions. All right, with that, I will hand it off to our presenters in the room, and I will share your slides and then pass you slide control. Let me see. Okay. So I'm passing slides control to the little clicker.
Looks like whoever's talking forwards, backwards. Yep, that's forwards. Yep. And then just whoever's speaking at the time, just in the mic.
Hello all. I'm Radhi Preeti. My teammates and I, we are undergraduate students from National Institute of Technology, Karnataka. This is our first time at IETF, and we'll be talking about some of the new tools that are available to test various congestion control and queue management algorithms. The first tool I'll be talking about is called CCPerf. It's an evaluation tool used to evaluate congestion control algorithms. And unlike other network testing tools, which are built directly to test against real-time networks, CCPerf is built on top of NS3. It provides various experiments with varying network and traffic conditions to evaluate the congestion control algorithms. And Okay. This is an exhaustive list of all the experiments that are available in CCPerf. And as RFC 9743 states certain evaluation criteria for a new congestion control algorithm, it states that in one of its evaluation criteria, it states that uh, any new congestion control algorithm should be compatible or should be tested against already existing standard and deployed algorithms. So as we can see here under the competition experiment, we have three tests which states about Reno friendliness, cubic friendliness, and Vegas friendliness. So all these tests in CCPerf evaluate how a new congestion control algorithm will work when it's working with all these three algorithms. So we have experimented all the experiments that are listed in this slide, but due to time constraint, we'll be going through only the response against pulse wave experiment. If you have any, or if you like want to discuss in particular to any particular experiment, please reach out to us, and I'll be passing on to Suprada to talk more on the hackathon results and the experiment of response to pulse wave.
Hi all, good morning. So I'll be presenting about the hackathon results. We observed some interesting facts and we want to share them with you. So our objective was for the hackathon where we wanted to set up NS3 and CCPerf, and then we wanted to test two Q disciplines, FQ Codal and FQ Pi. And then there was also a draft about rate limited sender, which was completed by one of our remote participant. And then there was another draft which was a modification to Codal, which will be also completed. And then so our main goal was to test congestion control algorithm. So here is one of the graph that we have presented, that is TCP BBR. So we can see we have three plots available. One is in-flight segments, one is throughput, and one is SRTT. We did not analyze these graphs in detail because our focus was more on testing Q disciplines during the hackathon. So I've put up this graph right now because we also saw there was one presentation about BBR happening today. So this plot may be helpful for that. But I'll be discussing FQ Codal and FQ Pi plots in detail. So before that, let me explain what is response to pulse wave experiment. So in response to pulse wave experiment, the main idea is to oscillate the bandwidth between 32 Mbps and 16 Mbps. So as we can see in the graph here, the dotted line there, the darker dotted line basically shows the 32 and 16 Mbps bandwidth. And we can see in this first graph that our in-flight segments in Codal, FQ Codal, are a little less than 32 Mbps, which basically means it's not utilizing the bandwidth completely. So correspondingly in the throughput graph as well, we can see that our blue line is a little lesser than the dotted line. And again, correspondingly in the SRTT, it's obvious that since it's not utilizing the bandwidth completely, the SRTT remains less at 15, which is the base. And then when we move to see the Mbps at 16, we can see that it is the blue line is above and the throughput is exactly at 16. and the corresponding SRTT rises because first we have a bandwidth of 32, and then when we decrease it to 16, the in-flight packets will basically get queued up in the buffer, which leads to a spike in SRTT. So this is the observation we made, and we have the exact similar graph for FQPy. So here we can see that in the in-flight segments are in the second lap are a little more than the dotted line. The blue line here goes above the dotted line, which means that the bandwidth is being utilized much better. So in the throughput also, the second loop, we can see that at 32 Mbps, it's being utilized properly. And then when it is at 16, also it is being utilized properly. So basically the blue line and the black line are kind of overlapping, right? So again, the same thing in SRTT. We can see that SRTT is being maintained at 15, which is the base, when the bandwidth is 32, and when the bandwidth is 16, we are seeing spikes, but that's all right. So this was the observation we made. We hope that is helpful, and also please do join us at the presentation of the draft of FQPy in the TSVWG tomorrow. Thank you. Now I'll pass on to Shreya.
So, hello everyone. I'll be introducing the second tool to you all. The second tool is Nest. It is the network stack tester. It's a network emulator that runs on Linux namespaces and helps us emulate networks and create and configure network testbeds. This tool was actually created by and currently being maintained by NITK students alongside our professor Mohit Tahiliani. Some of the features of Nest would be it allows us to use APIs that help us generate plots and visualize data of the network tests. It also provides APIs to configure TCP parameters such as slow start, restart, TCP fast open, and window scale options, to name a few. Nest is also one of the only few congestion control testing tools that allows us to test multi-path TCP. And it also provides emulations for co-op as well. Nest also supports emulations with MPEG-, SIP flows, and routing protocols such as FRR and BIRD. If you would like to know more about Nest, you can click on the link in the slide deck and download it from the GitLab repo. Now I'll be passing it on to Anuhya.
Good morning, everyone. I'm Anu here, and I'll just be showing a quick examples of what we can do with Nest. So as you can see on the slide, it's a built-in example for MPTCP topology, which is already there in Nest. So there are 6 hosts and 6 routers. And as you can see, there are H1, H2, H3, H4, H5 here, and H6, and the routers in between. H2, H3, and H4 have 2 paths connected to the single system. So no other tool as of now can emulate and show us MPTCP, so we can quickly test MPTCP with this. And the next slide shows us the graph for Nest TCP BBR, and we are seeing how aligned it is to NS3 BBR's output. So as you can see, they're quite similar. So by this, we can tell that Nest produces good results for different congestion control algorithms as well. So please do check out Nest. Thank you. Any questions? Okay then, thank you.
Stays. Go for it. We got a few people had to take time to join the queue, so give them a second to get to the mic.
I don't have a question, but I'm really thrilled to see you all on this stage. We talk about newcomers, you talk about diversity. This is what it looks like, and I'm really, really inspired and hopeful for our future. So thanks for coming and presenting, and I think I'll have a good look at it. My background is actually making tools like this, So I'll definitely talk with you guys and know more about it. Thank you.
Last second, Mozilla. Yeah, so in a second, what you just said. So if you're a professor in the audience, right, these could be, why aren't your students up there talking about the cool stuff that you're doing, right? So Mohit is doing a really good job getting his students here, which is great. And this is an interesting presentation. So I mostly work on Quick and not TCP. And so I was wondering as I saw that, because there's a lot of things here that I immediately want for my Quick stack. So I wondered if anybody was looking into how you could support different quick stacks in this sort of tool.
Hi, Mohit. I'll take this question. So out of the two tools that we presented, as you see, one is CCPerf. And unlike the other tools like what we have, iPerf, HTTPerf, or NetPerf, this tool is built on top of NS3. And NS3 doesn't have a native quick model yet. But if we could build a native quick model for NS3, then possibly all the tests that CCPerf has can be actually used. Right. So long as Nest is concerned, we already have an open merge request on the GitLab repo. What Nest tries to do is it tries to use the existing Linux utilities and put them together in a Python wrapper. So what we have done is we have taken up AIO Quick because it's built using Python. So that library we have picked up, and we have an open merge request. So soon Nest will have support for Quick inherently.
Okay, that's good to hear. Quick stacks are all different, unfortunately, and so while it's great to have support for some stacks, I would really like. So I work for Mozilla on Firefox, right? So I want my stack in there, and I'm willing to do the work on our side. But so I've looked into NS3, for example, right? And you're correct; they don't have a model at the moment, and even if they did have a model, it probably wouldn't implement exactly what we implement.
Yes.
And I want to like diagnose our bugs, right, and not some generic bugs that somebody else might have.
Okay.
And there was this sort of, it was called the network simulation cradle. I think there's a different name
NSC,
now.
yes.
Yeah, and I have not been able to get that to work at all, unfortunately. And I don't know if anybody has been successful, but at first I was very excited because that seemed like a way to get your quick stack plugged into NS3. But have you guys have any success with that?
So NSC is quite old. We actually use these days direct code execution, which is called the NS3 DCE.
Yeah, and that's the thing I couldn't get to work.
That's
the thing I could not get to work.
Oh, okay, I can help you with that.
All right, thank you.
Okay, yeah, thanks.
Thanks for bringing this to the IETF. You know, I'm always a little bit skeptical of. Sorry, Ian Sweat, Google. I'm always a little bit skeptical of simulation frameworks, but based on what I saw here, I like the fact that you're thinking about like a wide, diverse set of situations, and like, you know, sometimes there's different AQMs, and sometimes they're ECN, and sometimes there's not, and you can have different like all the combos and all the different kind of flow things. I was actually though particularly interested in video delivery and BBR and other congestion controllers. And I think you mentioned Dash. You had some sort of Dash simulation at some point. Yeah. I'd be fascinated to see more about that, since that's obviously a use case near and dear to my heart. But you know, maybe for another time.
Thank you.
Ingemar?
Good morning, and thanks for presenting this. And I was see you looking at your new CCPerf, and I believe what is perhaps missing is being able to try out with L4S, which is a kind of a new kid on the block around this packet marking and AQM. That would be really welcome, I think, for even more testing. And of course, you mentioned with different congestion controls. We have BBR. You mentioned that is that you tried out, but also if you really like it, you can try with Scream, which is a congestion control that is brought up here in the CCWG group. So. That's about it for me.
Thanks, Ingemar. So about the first point about being able to test L4S, that's possible to do in CCPerf, because CCPerf is a framework on top of NS3, and NS3 supports L4S for all its modules. So the FQCodal implementation in NS3 as well as the FQPy implementation in NS3, both of them have L4S support. So there's a Boolean flag that we just need to turn on, and then CCPerf would be able to perform experiments with L4S. So yes, that's possible. Second, thank you about recommending to test it with Scream. The only limitation that I could see over there is that we will need an native model of Scream for NS3 to be able to test it with CCPerf. But if that's available, we'll be more than happy to use CCPerf to test Scream. But yeah, thanks for the inputs, anyone.
Very nice. Thank you so much. I know we've been talking a bit, especially as we've been getting CCWG off the ground, about kind of doing more at the hackathon and having additional ability to do some of that testing for folks so that people who wanted to propose changes aren't also under the burden of doing all the testing themselves. And this is a really big part of making that happen. So extra thank you for that. Next up, I believe, BBR.
Thanks. So I'm Ian Sweat. I'm here to talk about BBR and an update. Oh, thank you. Neil and Joseph are also editors and authors on the draft. And I believe they're on the call in case you have any questions that I can't answer. So we'll outline some recent updates, summarize some open issues and PRs that we need some feedback on or would like some feedback on. Some of them were quite straightforward and editorial, but still need to be fixed. And also talk about kind of what's the future, what's the path towards actually getting to RFC. And obviously, if you haven't read the draft already, please do so, and either email to the list, file an issue, contact us directly, whatever makes sense. So here's an outline of kind of the history of BBR. I think best to say these are a pile of links if you want to go through kind of the past. I don't need to read them all out. But yes, we have been actively kind of getting it into more, convert to Markdown and do other things to make it kind of more like a typical IETF draft. So past slides. So the main changes are we were missing some pseudocode. We just never bothered to define a method. Someone kindly wrote a PR to define that method. There was kind of a subtle bug in one of the pseudocode. There's some editorial text to try to remove the number of times we mentioned TCP and SAC. I think it no longer mentions SAC at all of the draft. So that's part of this process of making the draft slightly less TCP centric. We renamed in-flight low and in-flight high to in-flight short term and in-flight long term. For those who are familiar with BBR, these are two state variables that their names are potentially confusing because in-flight low can be higher than in-flight high and vice versa. And I think almost everyone the first time they read it assumes that obviously in-flight low should be lower than in-flight high. That is not true. So really a more accurate name is like one of these is a short-term variable and one of these is a longer-term measurement of kind of like what is the safe BDP or like number of bytes in flight. So again, we did find acknowledged and delivered in a more transport agnostic way in an effort to move away from being quite so TCP centric. So go. As we evolve the BBR draft, obviously we want it to be clearer. This is a fairly complex algorithm. The clearer we can make the text, the better off everyone is. We would like to simplify it, although I think we're also hesitant to make large changes without some amount of testing and simulation. Obviously, improvement in coexistence is a goal, performance, and avoiding kind of any regressions with the changes we make. Honestly, I think from my perspective at Google, I think we're quite happy with the performance in the vast majority of situations today. But there are situations, it's not optimal. One thing that I'm interested in feedback from this group is kind of what exactly is the bar for publication. So I would propose that we want multiple deployments at scale in both Quick and TCP. The text should actually be implementable. We should be able to implement from the draft alone and not have to go read the Linux source code, which is, I think, what most people do. And fair sharing with other BBR flows and coexistence with Reno and Cubic. But my thesis is it's better to publish a good draft that has real deployment experience at scale in a reasonable time frame than keep evolving BBR indefinitely. I think there are, and people can feel free to disagree with me about this, but I would rather not repeat the Cubic situation where by the time we publish an RFC, it's kind of irrelevant. There are two open PRs for minor algorithm changes. One is basically like, there's theoretical derivations that say we should be using 0.5 in some case, that we're currently using 0.35. We are currently using a BBR drain constant that is based on the pacing rate, not on the congestion window multiplier. There's a really nice analytical derivation that says why a half is a better number. We don't have basically we have no data as to like really whether it's better or worse at the moment, unfortunately. We're kind of due to reruns and get some production data. And I think that's the only real thing blocking us making this change. But like from a theoretical architecture perspective, 0.5 should be better than 0.35. So I don't think that's controversial, but if anyone wants to provide data in the real world, we would more than welcome that, of course. And then removing the ACK phrase from the pseudocode kind of simplifies the algorithm. The move fast implementation already does that. It, in theory, makes the algorithm almost, it's unclear if it's basically functionally identical without this, or it's almost functionally identical, but mostly it's kind of just a simplification. Take a look if you're, especially if you're an implementer and like this kind of minor change, but it seems like an reasonable one. And again, more data would be great. Generalization on TCP transports. So as I said, I removed some SAC languages and other things, but bandwidth estimation, I realized it still uses a bunch of variables with _SEQ in them, sequence number. Quick does not have sequence numbers. So obviously that variable is probably not the right name. But it also points to the fact that maybe larger changes need to be made. I haven't focused on the bandwidth estimation text quite as much. Obviously I will be working on that. But if you read the draft and you see things where you're like, oh, I found yet another thing that isn't that issue, that is too TCP centric or is otherwise like unclear, whether it isn't for any non-TCP protocol, please file an issue, tell me, add it to that issue, whatever you'd like to do. So. Another issue is whether to do probe RTT every 5 seconds or 10 seconds. MoveFast has some data that indicates that making it 10 seconds is better. It used to be 10 seconds for BBR. Then, as it says here, when we changed the probe RTT drain from 4 packets to 0.5 times BDP, that at the same time, we have the time scale under the theory that like the net amount of, basically amount you're draining the pipe is the same between the two. It's not really the same in certain cases, especially really low BDPs, but that's like a side project, so let's not go there. But we have some empirical data that probably 10 seconds is better and it doesn't really seem to cause any harm. I think at Google, we plan to try to run experiments to kind of verify that, yes, that does not cause harm, and we're going to run some simulations. But again, this is a case where I think simulated data would make me probably just as happy as production data, because I think we already have enough production data to say it's probably better in production circumstances. So if anyone wants to do some fun BBR simulation work, this would be a perfectly nice case of an A/B comparison that where I actually would totally trust simulation data as being a valid comparison. So editorial issue, we now use in-flight and in-flight and in-flight in 3 different ways. It's not really a big deal, but it's a little bit annoying. RFC 9002 almost always uses in spaceflight. Sadly, it does not always use in spaceflight. Sometimes it uses a dash. That was my bad. We should probably standardize one. I was kind of inclined to go with in spaceflight. This is one where if anyone in the room has an opinion, like, please speak up now. Okay. No, Corey just gave me the like, I do not care at all look. Okay. Probably I will go with in spaceflight unless someone objects and move on, but figured I'd bring it up. I opened this issue a bit ago because I had done some experiments by just getting rid of in-flight short-term entirely. The rationale at the time was because reasoning about how BBR works is already complicated, and the more kind of constraints on the system, it's difficult to figure out like how this constraint interacts with the other like 4 constraints in like the parameter space. And I did some experiments that kind of showed like if you just don't use it, it's not really that bad. But Neil rightly points out that the short-term, that mechanism is there to like deal with cases when there's a rapid reduction in bandwidth, in particular like a rapid reduction in available like BDP or like buffer depth. And so if we got rid of it, we would probably want something else that could accomplish the same goal of like, how do I make sure that like my excess in flight is tapered down quickly in cases when like the amount of available buffer depth shrinks. Coming up with such a mechanism as possible is not trivial. And so going back to the previous slide of like, we'd like to ship this, you know, sometime in the not so distant future, unless someone has an obvious solution. I think the current opinion of the authors, including myself, is we should probably just keep it because it does accomplish the goal it is intending to accomplish. And inventing a new mechanism at this point is not trivial. But it's still an open issue at the moment, but I think the intention is to close with no action. But if people have thoughts on this, especially those that have implemented and looked at the algorithm a lot and looked at traces, you know, we're open to feedback, obviously. All right. Decide the document's stance on ECN. So here, there are a number of questions here. You know, do we want to document a recommended response to ECN? The challenge at the moment is that we do not have any large-scale real-world testing of BPR with any ECN response over the public internet whatsoever. I'm not sure if anyone's even done small-scale testing. The concern of the authors is that if we wait for that to happen at scale and get enough data, that we could be waiting quite a while. As an author, I think my recommended way forward is, and I was going to write this text up, but I haven't yet, is basically to document, you know, cite the relevant RFCs that exist, say like if you negotiate ECN, you know, you should or must, you know, at least conform to the principles of what is in those documents, but not prescribe a specific way to conform to those principles, because at this moment, I think I would have to still consider that research in this context. If people have another recommended way forward, I'm happy to hear it. Or if you know you want to go over the details of exactly like what's a must and should, I'm also happy to do that, and we can go over it on the PR as well. So next slide. Oh, that's me. Why am I? All right. Please read the draft if you have not. You know, offer. You know, contributions are always welcome. Data is always welcome, both simulations and non-simulations. And yeah, if there are any major changes one might want, this is leading into probably what Christian's gonna say, in the draft, knowing about them sooner rather than later. So like as authors and implementers and deployers, we have more time to like try to implement it and potentially test it in the real world. That would be enormously helpful, just so kind of knowing more about like what the work that is remaining now would be better than later, just to make sure we have kind of a clear path towards completion. Thank you.
Thank you. All right, we have a couple people joining the queue. We also just kind of did a whirlwind through a pile of issues. So I'm wondering, would it be helpful if we backed up a bit and kind of went through them one by one and let people jump on the queue button as we as we get to each thing. And if there's ones that people don't have tons of thoughts on, we'll just skip through. I think your first one was around just kind of what is our threshold and bar for publishing things.
Yes, yes.
Yeah, right
That's
here.
this one. Yep. That's probably the most important one, honestly. But
Cool. So let's start with that one. Christian, if that was the thing you wanted to talk about, then wonderful. Otherwise, please re in queue. All right, Martin, you are up next.
Sorry for going too fast.
Oh, it was great. Thank you for having so many slides and making such good progress.
Martin Duke, Google. I think, I believe Reese is covering me on notes while I'm here. Thanks, Ian. First of all, can we go to slide? Oh, this is great. Perfect slide to be on. How close do you think you are to meeting this bar? First of all, I support the bar that you propose here. Secondly, how close do you think you are to that time-wise?
I think if the issues that are open today, modular editorial issues that I'm sure will get filed, are all the issues we're going to deal with. End of the year for working group last call. it's pretty soon because we went over all this open stuff. Now, if we want to open up, again, this goes back to the do we want to open up larger changes? I think farther out. Neil is on the call as well. And so Joseph, if they would like to speak, I'm happy to hear their perspective, but I think end of year.
Okay, cool. Second thing, regarding it being experimental, I think that's good. It sounds like, we don't feel like we've perfected this yet. So let's do an experimental RFC and then later we'll perfect it and do a standard. That's a great plan. But with 9743, strongly suggests that experimental draft should have an experiment in it. So you may want to add a section for that. And then finally, at the risk of having our usual Google meeting here at the mic, as you know, I'm conducting some large-scale ECN tests, but on Cubic right now. I think if you, Neil, and I could get together and figure out what we want to mess with for BBR, I could probably do that simultaneously within the year timescale you're thinking of to finalize this thing.
I do agree that I think one implementation, ours or otherwise, can get probably reasonable scale deployment of ECN testing.
Yeah.
I worry about two things. One is still penetration of the ability for us to actually negotiate it end to end and a large enough substantial fraction of flows, which I think we don't know at this point, especially for L4S. And then my other concern is say we finally cool, we're happy with this. It's, the time frame for that being adopted and tested in multiple other implementations is longer. And I think the path towards TCP L4S on the public internet, last time I checked, it was not in the 1 year time frame. And someone should correct me if I'm wrong. So I don't think there's a possibility of us getting at scale data for TCP L4S within a year, certainly, and maybe within 2.
Or you could do it for quick though.
Right, yes, so it would only be quick. So I don't know how, it's probably fine. I'm just pointing it out.
And to beat on the point of can we put ECN stuff in this? Do we feel comfortable with just ECT0 just treat it as a loss? ECT0 CE rather, to be more precise?
That seemed plausible to me, but I think if Neil's on the call, I think Neil had some very good points about it, and I can't remember what they are. And so I apologize.
All right, thank you.
We have a slide later for that one, right?
Huh?
We have a slide later for that one.
Oh.
I think.
Do we?
Do we?
Okay, well, Neil's in the queue.
No, stay on where you are.
I've taken enough time. Thanks.
Yeah. Anything else on our bar for publication and that kind of stuff, or we'll start going through the individual issues? Let's see. Corey's in the queue there. Lucas, you're in the queue. Is that for this one or a later one?
Just for this one. Just following, excuse me, Gory Fairhurst. So just following up on the you've got a lot of different things to do here. And it's really great just to get this published as experimental. So I like that you're going to get that done quickly. But we've got some probably simulation tests for weird things which you can't really check because you're testing for the outliers.
Sure.
The harm to other things. So you've got to somehow get feedback for those. So I guess we need to really encourage the group to make that feedback. And That's not easy for people to do on a spec that's kind of evolving. So I don't know if you have a strategy for how we get that feedback. And then you're going to implement, which is obviously fairly well done. And then you're going to do some real deployment experiments. So hopefully that will get plugged in. And then there's a third element, which is kind of the ECN and other stuff, which I guess will probably become the experiment, is what I kind of hear, if you can't do it. But it's the first one, which is the curious one, which is getting people to somehow simulate and model this and encouraging people to do that.
Yeah, I mean, if I had my druthers, I would say, like, if people could describe and or ideally create some somewhat reproducible simulation results that they are concerned about and file an issue for that. Like in this particular case, I consider this really, really bad. Then I think as a group, as well as authors, like we can kind of go and say, like, how bad is that compared to like the status quo and like the current wards of cubic and other things, which also has its own problems. And then also say, like, is this a problem that like we can mitigate at least with like a reasonable amount of work, or is this like, this is just like cost of doing business and it's like fixing it's borderline intractable, at least based on what we know. So like, this goes back to the whole, like, if I know all the things that people are concerned about and have like a big list, then we can be like, no, yes, no, maybe, like I'll try or something. But that's my preference. But I mean, we can interact in a number of ways. But the earlier we know about those, again, the more we can kind of holistically say, like, these are the things that like we think we can improve, and these are the things where, maybe we can provide some cautionary text that like, I mean, I don't know if I don't think the draft has it today, but like there should be cautionary text probably that like, this is still not an appropriate congestion control algorithm for like real-time video conferencing. It's just not. Like, you could do better. It's not the worst. It's better than Cubic, but like, it's not good.
So I think you said you're looking for people to file issues that might be tests, that might be things that you have to consider. Is that right?
Sorry, what?
You're looking for people to file issues about the sort of tests that they think you might need to consider. Yeah, okay. I like
yes,
that.
Ideally, if you could link to a presentation or test results, like link to like someone running the test or you running the test or a repro running the test or something as well, and not just like, I'm concerned about X is a little too vague. If it could be more specific, so we can kind of like, yeah, that'd be much more helpful.
Looking for as concrete as possible.
Yeah, as the more like, I mean, it's kind of like, if you file a bug, can you please give me a repro test case? Like, I'm sure I might be able to come up with it by myself, but like, please don't make me.
All right, Lucas, you're up next.
Yes, I just on the thesis, I think this is a good thing to do. Just like get it done, please. It's been waiting ages, and as someone on the periphery of congestion control stuff, like when I'm speaking to others who are even further out, it's just like it's really hard to explain what's going on. And actually, there's a load of good work that's happening, and I'd really like just to draft to point them to. So, yes, let's have this bar and just publish something. But I think the ECN discussion is maybe in friction with that. Like, ECN is cool, great, yeah, but like as an implementer, we could probably do the simple BBR stuff, and then the ECN thing is going to get gummed up in, well, need to go and speak to another team who can make sure that something in the network is doing this or not, and debugging it, and it's a distraction from this kind of core basic capability. So if it's an experiment, the experiment is try it without ECN, and then find out that it could work better with ECN or whatever. It doesn't stop anyone doing it. I don't see why we couldn't come back in a year or two's time and update the document or whatever with more ECN findings. Like, that's the approach I would take, because otherwise we're not going to achieve this bar or this thesis of a reasonable time frame. That's my concern. Others might disagree. That's cool, but yeah. Thanks.
Thank you, Lucas. Anything else on this slide before we go through the rest of the issues?
Yes. So I heard a couple of things there that are not listed in the goals, but maybe should be. Ian, you said that real time is not a goal. If it is not, I'd like you to be very explicit about it, because it would make my life simpler.
I think my comment would be, and you've done a lot of work in this area, Christian, so this is sort of like inside baseball, honestly. But I think there are changes to BBR that we can make that would make it better for real time. You have pointed out a number, and a few other people have come up with ideas. And this goes back to the, like, if we decided to pull that work into scope for this draft, I'm a little concerned about like the time frame of like trying to sort all those out. That does not mean I'm not very interested in those changes and optimizations. And so that's a great example of, like, I think the working group has to decide, like,
yeah, no, look, I understand that you have to cut a bunch of bugs in order to make the deadline. I mean, I've done that many times. That's fine. But that means that well, on the other hand, I mean, I do have to ship products that use congestion control with real time. So far, we have worked on BBR because it was definitely less awful than Cubic or Rhino.
Yes, I agree.
There are a lot of sharp points in BBR that would need work to fix. I understand very much that you do not want to fix them right now. That's a very legitimate program management decision, but be very explicit about it, because that means that basically if I cannot solve those points using BBR as stated, I will have to be using something like a Christian's version that is doing this or that, and not be held accountable that, hey, you're not doing exactly BBR.
Yeah, that's a good point.
That's one point. The second point on your objective, you have an objective which is better coexistence with Rhino and Cubic. And on one hand, that's correct. On the other hand, that has some pretty negative results. Because doing coexistence with Rhino and Cubic means that you want to limit the period of your feedback to what Cubic does, which is something in the order of 30 to 60 RTTs, depending. I mean, we can read the paragraph. And that sucks.
Yeah, it does.
And so we need to be very clear that that's also a point again, which is basically if we do better coexistence with Rhino and Cubic, then we know that we will not reply correctly to an improvement in bandwidth. And indeed, we see that in all of the simulation. Simulation people do some kind of a sawtooth or a crenulated simulation, and you see that, yeah, we drop to the bottom of the kernel really fast, but we never go to the top of the next kernel. And sometimes we wait a very long time before starting to grow. So that's a direct consequence of putting coexistence with Rhino Cubic as a top priority. It should be recognized, and again, be very explicit about it.
Yeah, I agree. I think you're making a very good point, which is it should be a consideration, but probably it should be towards the bottom of the priority list. It's like, it should be like, if it's good enough, it's good enough. And, if once we reach whatever we consider good enough, after that priority should be given towards things like, more rapid adjustments, changing bandwidth or white size. I mean,
some of the choice from BBRv1 to BBRv2 or 3, including this business of waiting like 60 RTTs in cruise mode, that's horrific if your bandwidth increases.
Yeah.
And that's directly tied.
So.
Yeah, and that's about it. I mean, the other part is be much more clear about app limited behavior. But it's
yeah. Actually, Christian, would you mind filing an issue? And if you don't, I will try to remember to do so, about like some of your concerns, particularly about like documenting that there are some sharp edges in BBR as it's described today, particularly for real-time applications. I mean, app limited behavior is an obvious one that I am very aware of. That
there's app limited behavior, and there's basically 1 RTT of piling up data if the link drops.
Yeah.
which is the other very sharp edges, and the third one is some excursion at the end of slow start.
Yeah.
The three big ones. Yes.
I think you've given us.
Yeah, I'll do that.
Okay, thank you. I was going to say, I think you've given us another area where like marking this draft experimental is appropriate, which is to say, there have been a number of proposed improvements to deal better with app limited behavior and a number of things Christian's mentioning. And, we need more time to kind of work through those, understand them better.
Okay, thank you.
Thanks, I appreciate it.
Thank you, Christian.
So Richard Schaffnegger, just a quick comment on the ECN part. If you want to publish this draft quickly, then perhaps it's better to shelf the specifics about ECN for a later date. And I just want to reflect the same sentiment that many of you have expressed. Some of the longest running drafts have been concerning themselves with ECN. So waiting for experiments around ECN and then putting it into this draft will just prolong the publishing date. So again, something that could be done here as an experiment, yes. Mentioning also okay, but don't wait for this with ECN.
Thanks. Yeah, I don't know if it's the expectation of the working group, but I was under the assumption that as soon as BBR was published as an RFC, probably a BBR BIS would be started as a draft as a follow-on, and ECN would likely be in scope for that. But I don't know if that's the current thinking of the chairs as well.
Yeah, so we haven't talked a ton about that yet, but going along with this thesis here, one of the things that we have been spending a lot of time talking about is that if we thought we had solved this problem, we would be done and we would all go home. And so the expectation is not that we wait until all of congestion control is solved with the current version of BBR, but rather that these things tend to kind of go in cycles. So we should have a good jump forwards. We publish that, we get some experimental results from it. We get actual deployment experience with it. We take those learnings and, a year or two later, we do another version that says, these are the things that we learned. I don't think we ever expect that we're going to stop learning this. And part of the reason that we're all here is so that we can share those learnings with each other and come out with something that's better. So, all right, let's keep going through here. I saw Neil, you're in the queue.
Yeah, let's see. Can you hear my audio?
Yes, we can.
Okay, great. Hey, everybody. Yeah, so just a couple thoughts on some of the issues various folks have raised. So one of them was this question of how BBR could treat ECN signals in the case of ECT0. I suspect that Martin is probably right that we could probably do some things straightforward in the timescale of maybe a year, and if everything went well, we might have some sort of answer, because I think there were some pretty reasonable ideas in the discussion on the GitHub issue. For example, basically BBR v2 or v3 have places in the algorithm where you just need to plug in a signal that tells you, hey, that's too fast, or a signal that says, hey, there's been some kind of congestion. And, for ECT0, it doesn't provide you a lot of information, but it does provide you that level of information that, hey, that's too fast, or there has been congestion. So it does seem feasible on some time scale, but I kind of like the idea of this most recent turn of the discussion here, where Richard and Ian, I think, we're pointing at, maybe we should just try to ship kind of what we have now without the ECN story. And then as soon as we've finished that version of the document, we could start a BBR BIS right away that is trying to actually build an ECN response story. That sounds appealing to me as well. Let's see. Corey brought up the question of testing and testing for coexistence and harm to other flows. I agree that's important. I just wanted to point that there are some nice approaches that people could use, and if people are interested in pitching in. So there is for example, the Linux TCP BBR version 3 that's out on GitHub, that corresponds, as far as I know, directly to what we're running for Linux TCP for google.com and YouTube. So people can run real experiments with that open source implementation. That should be a complete implementation. And there are various tools that people could use for that. So for example, I think the second tool that was presented today, which uses Linux with network namespaces, I imagine that could be used with the Linux TCP BBR3. Our team also released a tool kind of similar to that in spirit called transperf a few years ago, that I'll mention in the chat thread after this. Let's see what else. So Christian made some great points about qubit coexistence, where it's very tricky to coexist without qubit without inheriting some of its bugs, in particular, its sluggishness to responding to newly available bandwidth. And right now, BBR v2 and v3 are very conservative in the way they're responding to newly available bandwidth. I do have ideas about how to improve that, and I'm working on lab experiments. But again, this would be something where it would be kind of like ECN. It would be a question of how long we want to wait. And again, we might want to kind of try to document what we have, as long as there's a consensus that it's good and safe enough or reasonable enough, rather than making these particular improvements to the rate at which it accelerates, that kind of thing. Yeah, so I think I caught all the nice issues that people brought up, on which I had some thoughts, but thank you.
Thanks, Neil. I wanted to follow up on one comment that Neil made that I think is actually really important from the perspective of helping the working group contribute to this, which is if you're going to run NS3 tests or something, please do not use what is in mainline Linux today. Please use whatever Neil has on GitHub. The gap is substantial, and I would hate for us to go through a cycle of issues where BBR has this behavior. It's well, it used to, but it doesn't anymore. And just kind of, that is an unfortunate use of time for everyone involved. And I know it's more annoying to use the non-mainline Linux version, and I appreciate that. And I know Neil is working on upstreaming a number of things, but please do try to use tip of tree in that particular case if we're filing issues, and especially doing simulation testing.
Hi, my name is Alexander Azimov, younger. As far as I remember, at some point of time, it was supposed that next version of BBR will be coming in two flavors. The first flavor for the wild internet, and another flavor, which was BBR.Swift for the DC infrastructure. I wonder what happened with the second part of the project.
Are you speaking of data center version, you're saying, or the
So as far as I remember, it was in Neil slides a few years ago, maybe a year ago, I don't remember exactly. And it was called BBR.Swift.
Oh, .Swift, yes, that exists. It's never seen the light of the public internet, to my knowledge. Can I let Neil answer that question, because he's an expert on that, and I am not. There's not for example, there is no BBR Swift implementation, to my knowledge. Certainly in any quick implementation I'm aware of, and I think maybe the only one is in the internal TCP implementation at Google, but I'll let Neil answer.
Yeah, that's exactly right. Yeah, so far we haven't open sourced BBR Swift for sort of two practical reasons. One is that it depends on particular TCP timestamp option support that is non-standard, and so there would be either the ugly process of upstreaming a non-standard TCP option format, or the sort of very labor-intensive process of standardizing some new TCP option format, or at least getting a draft far enough along that the Linux open source community felt comfortable supporting the new option timestamp format in Linux. So those are the main reasons why we haven't upstreamed it, what we have. We have a Kevin Yang, who's a team member who did the BBR Swift implementation and deployment internally, and he is working on a new version that is a pure TCP Swift that we do hope to open source at some point. Again, it has a number of dependencies, and so it'll take some time. But that's kind of the current status. The principles are all laid out well in the Swift paper from SIGCOMM 2020, and there's not a whole lot of extra secret sauce. There's no extra secret sauce, just a lot of blood, sweat, and tears engineering that went into it. It's not that we're trying to hold it back. It's just that there are a ton of dependencies to kind of get our ducks in a row.
Okay, thank you. It's great to hear that you are still kind of planning to open source it at some point of time. We'll be waiting. Thank you.
Miriam?
Mia Kulevin Eriksson. So on this slide, yeah, I mean, I agree we should at some point publish an RFC, not like work on this document forever. But one thing I was hoping when we adopted the document is that we actually can like pin a stick in the ground when we have something kind of more stable, which is not really what I'm seeing. I feel like BBR has been moving continuously the last, I don't know how many years, and it's still moving. And so the question is not like, should we publish an RFC anytime soon? The question is, what are the requirements where we can say this is the point of time where it makes sense to publish an RFC? And so since we adopted the document, I think what you've done so far mostly is kind of cleanups, which are really important to get like a document that is clear and understandable. But what we didn't do so far is actually talk about any of the choke points people are worried about with BBR, like fairness or what are the right thresholds to use and why, or in which environments. So I was hoping by having this as a working group document that we would actually find agreement on some of these points in the group before we publish something, rather than just take what's there and stick a number on it.
Yeah, so I would say some of the thresholds I think are well reasoned, and those are the ones that mostly have like mathematical derivation. But there are some magic numbers lingering around. At the very least, I mean, if you'd like to file issues and say like, why did you pick this magic number, or like at least explain why you picked this magic number, at the very least we can do that. But I mean, we can also, I mean, some of those magic numbers are not, like we could run an experiment with like a different magic number if we thought it was a better magic number, or like we had a better intellectual justification for it. And so like, I mean, the way that like a number of the derivation docs were written ex post. They were sort of like, we did it, and then we're like, okay, actually, let's do the math. And then we came up with a constant that was like very slightly different from what we first put in, but it was fairly close. And so like, I mean, we could do a similar exercise for some of the others potentially, and or like put better justification in the text about like why we did what we did. So, but yeah, feel free to file an issue. That's a great example of something.
Yeah, I do want to do
it.
it. I didn't put enough time in this for now. I'm just saying, like, we need to find, I mean, like, it's good to have an RFC out and have something that is stable and that people can use. But I also don't want to rush it too much, because I would like to get something out that's good. And I think to get something out that's good, we need to have something that is already kind of stable and that we can at least play a little bit with. And then we are sure that this is the right version that we should publish as an RFC. So I don't think, I don't want to stop us from moving fast, but I think we should also not move too fast.
So just to offer a couple of thoughts here, because I think you're highlighting something important here, Maria. One of the takeaways that the chairs have been looking at from some of this conversation is that there's a set of things that we need to decide as a working group, what is in scope and what isn't in scope for now versus next. And so I don't think that we've yet decided as a group, like, does ECN fall into that bucket for now or next? I've heard quite a few opinions for next and not a lot for now for that one. But I think the question that we need to answer together is, do we think we're in a place where we know enough to choose for each of the items in that list, and have we collected all the things that folks want to have in that list for us to choose about? So I don't think that we're in a space right now where we're saying all of these things are next, let's publish right now. I think what we're looking for, especially as feedback from the folks in this room, is what are the items in that list where we need to decide in this version versus in the next version. So please suggest those, please file issues for each of those. I think what we're going to end up doing after this meeting is kind of going through the set of issues and saying, these are the ones that we propose deferring to next. These are the ones that we think we still need to tackle now.
Yeah.
And then we'll kind of review that with the group.
Yeah, I will note that though it's not in mainline Linux, BBR v3 as it's been described hasn't really materially changed, I think, in like a year and a half or so now. And it's been deployed for, globally, on public servers as well as internally for like a similar period of time. So like, though we've been talking about a number of tweaks and stuff, like, changing a constant from 0.35 to 0.5, I mean, the scale of changes that we've even discussed in the last year or so have mostly been on that order. They've been like really small changes, the 5-10 second sort of things. For the most part, it's extraordinarily stable. Sure.
I mean, yes, I mean, that's good to hear, but still these small changes can have a big impact. And if you keep constantly changing stuff, then we never know where we are, even with those things, even if you just change a constant.
Yeah.
I saw Neil joined the queue as well, if you wanted to chime in. Oh, disappeared. Yeah, so Miri, I think that is a totally reasonable thing, and we are not asking that BBR stop iterating. I think that's kind of what we were saying earlier is this is not a fully solved problem. And so we are still going to learn things. We are still going to iterate. We're still going to share those learnings with each other. We're still going to run new experiments. That's kind of the whole point. And so we need to figure out where do we draw that line in the sand and say, okay, we think that we can converge on this. This is stable enough. This is worth upstreaming in all of the relevant places and putting the energy into actually deploying. Because I think that's really the reason that we don't want to have a weekly draft of what BBR is because of that activation energy to actually get it deployed, right? So we need to align on where do we think that balance is.
Yep.
Go ahead, Neil.
Yeah, thank you. Yeah, one thing I wanted to share is just kind of along the lines of what you just said, Eric, which I think was expressed nicely, which is kind of there's a balancing act of deployment and stabilization and allowing for improvements from the community and from the co-editors and such. I also wanted to second Ian's point that I hear the concerns about BBR being a moving target, and that is, while that is true on some level, as Ian noted, it's basically been the Linux TCP BBR3 has been there since July 2023, so almost 2 years, definitely well over a year and a half. And as Ian noted, the changes that we're discussing are fairly minor constant tweaks. And, these are kinds of things where, it's fairly straightforward if members of the community are interested for them to offer, emulation test results to sort of help the community make these decisions to sort of fine tune these questions of constants. I think Miria raised a really good question about the notion of fairness and coexistence, and I take Miri's point that there are some there are some real questions about what how good does coexistence with Reno and Cubic need to be before the community is comfortable with the draft, and I think that's an open question where we're going to need to come to some sort of community consensus, and I'm not sure exactly what the right answer is, and there are some real trade-offs as Christian was noting earlier. So yeah, those are just my thoughts at the moment. Thanks.
Thank you, Neil. All right, let's do a quick stroll through the individual issue slides, just in case anybody wants to jump for the queue as we do. So if there's any particular comments that folks want to make about the actual details here, we'll take a quick minute to just walk through each one. And then when we get done with that, we'll be wrapped.
So
all right, not seeing anything in the queue for this one.
yeah, this is this is the consistent the appropriately derived base and gain question where we determined analytically 1/2 is the right number. We have no data that really it matters which value you choose. It turns out, but yeah. So and then again, the other one was mostly an algorithmic simplification and how you describe the algorithm and document it. And it creates for easier pseudocode and potentially easier like actual software code. So,
not seeing anybody in the queue. Let's keep going.
Okay.
Beautiful. All right. We talked about each of these already, so it's mostly mostly just let's stick them on the screen. And
this is
I see
mostly an
Maria's
ask
in the
for
queue
people
for this
to
one.
re-review the doc. To be completely honest, is please point out cases where this is not true today, so we can improve it.
Yep.
Maria.
I'm Mia Kuhlmann again. I'm not have any comments on the specific issues, but I wanted to reply to you talking about fairness. So because I think that's one of the main points this group was interested in working on this algorithm to make sure we have the right balance there. Of course, you don't need like full fairness to renew in TCP. That's not the goal here, but like what's the right point exactly that. So I would really appreciate if we could use a session in future to dive a little bit more deeper into this point, figure out what the trade-offs are and where we want to settle. And also document that then clearly in the draft so people understand where we ended up.
Sure. All right. Good point.
Any thoughts on probe RTT intervals? Beautiful. Oh, this is a fun bike shed.
Yeah, no one seems like. I'm surprised no one went for this bike shed.
Yeah, well, yeah. I mean, probe RTT interval is one of the sticky points in a real-time application, because having your bandwidth go south every 10 seconds is really bad. So
you're saying for probe RTT?
Yeah, so 10 is better than 5, but 10 is already horrid. So it'd be very nice if there was some kind of a signal to not do that.
Yeah, the draft does have documents the fact that if you completely drain the pipe, you don't for enough time, you don't have to do probe RTT, which works great for like Dash style video playback. But it in no way, shape, or form helps the like real-time video conferencing case, because in that case you rarely fully drain the pipe. And so if that's the case you have in mind, then yeah, probe RTT is not your friend. At least as it's described today. I mean, it never has been. Making it 0.5 instead of 4 packets is certainly an improvement, but it's pretty brutal on real-time flows, and it's certainly a challenge.
Yeah. Okay, but I mean, I think we agreed to not handle that, so I'll stop.
All right, Neil and then Miria. Let's keep it snappy.
Yeah. So on the probe RTT point, I obviously agree with the issues with probe RTT and real-time traffic. One thing I want to mention, if folks are looking for a good research topic, is that I imagine that there are adaptive approaches that would work well here. I've spent a few hours here and there toying with one, but you can imagine. So for example, if you have a flow going and you happen to notice that your RTT is already only 1% above your min RTT, that's probably a good clue that your amount of in-flight data is probably no further than 1% away from what the amount of in-flight data you need to refresh your min RTT. So if you see your RTT is only 1% too high, you can probably just cut your in-flight by 1% and then refresh your min RTT with only a sort of 1% bandwidth penalty. So there are probably, there's probably some version of that trick that would cut the, common case probe RTT penalty to be negligible. So that's a, research idea someone is welcome to run with and either as part of this effort or as a research paper. Either way would be interesting. But that's one of these things that would probably be appropriate for the PRR BIS, I mean the BBR BIS document rather than this version of BBR. Yeah.
All right, briefly, Maria.
try to be brief. So, I mean, I think this is one of the interesting points we should discuss a little bit more. My observation is from working on other delay-based algorithms like LEDBERT. In the original LEDBERT draft, we already discussed having, for example, multiplicative decrease, which is now in LEDBERT++, is something that helps you to get a better minimum round-trip time sample. And like my observation is whenever you use round-trip time for your congestion control, you need something like this. You need to make sure that you do probing right. So this is kind of a more general thing that you need. And I think this is the most brutal way to do it. I think there are other ways how to reduce your congestion control periodically in order to make sure you find the minimum round trip time. So this is definitely something you can work on. So there is trade-offs, right? Right now you're trying to kind of empty the queue completely very quickly and then ramp up very quickly again, but you could also try to reduce step by step, so you make sure you just like go under the minimum queue just a little bit, not like fully, and then ramp up or whatever. That takes more time, but maybe it has less impact on performance or whatever. So yeah, I think this is one of the points we could discuss a little bit more.
Thank you. All right, we talked about our bike shed. And anyone want to jump for the queue here? We talked a bit about ECN already. I think we're going to come back to that as a bigger topic. And there's our conclusion.
Yeah, so unless someone wants to talk about this, this is probably a detailed topic anyway. Even if someone does have interest in this topic, it's probably better to engage directly with myself and the other authors because it's complicated. Sorry.
Beautiful. And I think we were ending with a request for please go and this is a good time to read the document and file issues and things we think are pretty stable. I put a poll up on the screen. Go sign into MeetEcho if you haven't already. And just a quick show of hands to see how many folks have actually read a recent version. Doesn't have to be the absolute latest. Not that there are that many that we've read. Hey, thank you, Ann. Very nice. But yeah, so this is a good time to go do so. Give it a whirl. See how it is, send feedback either on the list or as issues or in person.
Yeah, please, if you read something and just are like, that doesn't make any sense, either because you don't know TCP and it sounds too TCP, or just because it's like, this is incomprehensible, please just file an editorial issue and be like, I don't understand what this section is trying to tell me, and I will try to fix it, or one of the others will. So, you know, that happens. These things are complicated. We're trying to make them less complicated, or at least describe them accurately.
Thank you so much, Ian.
Thank you.
All right, brief stretch. Everybody ready to shift gears? Love it. All right, up next, let's talk about some rate limited senders. We've got Mohit, and I've got a clicker for you when you get up here. And give it 1 second. It should now work.
All right, hello everyone. So I'll be giving an update on the draft about the increase of the congestion window when the sender is rate limited. This draft has been adopted after the IETF 121. So thanks to the working group for adopting this document. So this work is being done by Michael, Tom, Gauri, and me. Michael is with us online and Gauri is here. I'll just give an update as to what has happened after that. Before that, just a quick overview of the draft in case there are people who have not looked at it earlier. So we have defined a new variable called the maximum flight size, which is the largest value of the flight size since the last time the congestion window was decreased. And if the congestion window was never decreased, then it's the maximum value of the flight size since the start of the transfer of the data. And the most important section in this internet draft is section number 3, where we have proposed 3 rules, which are here. And all these rules apply particularly when the flight size is less than CWND. So what has changed since IETF 121 is, the first one is just some wording improvements to the 3 rules that I had in the previous slide. We also noticed that we had not defined clearly some of the variables like N, SMSS, CWND. So we just did that. We also added an example in section number 3.1 to make it easier for everyone to understand this draft. And of course, I got added to this particular draft after IETF 121. We had some good suggestions coming in the mailing list. So the next step, I have a question here for the working group to help us understand. So we got a feedback from Martin mentioning that the draft looked good, but the first rule was a bit weak. And we did have a discussion and we felt that was a good feedback. And we feel that there's a question is that, should we remove rule 1 and make rule number 2 as a must? And will that actually, help simplify the text? So that's one of the things that we are discussing and looking forward to incorporate in the next version of the draft. We also had a suggestion from Neil on the mailing list mentioning about the usage of the word rate limited. So we think we should actually define this word properly in the draft because from the discussions and also from RFC 7661, what we noticed is that the word rate limited actually includes, when you are really limited by the CWND growth or, you are actually receiver window limited. And it could be either one of the flows. But when we use the word application limited, it probably excludes being limited by the receiver window. So I know we also looked at what RFC 7661 says about the word. So it says a rate limited application will experience periods when the sender is either idle or unable to send the data at the maximum rate permitted by CWND. So we plan to probably define this more clearly in the draft. But yes, that's the brief update. That's the link. We request you to please take a look at the draft and let us know if there are any further improvements that we could make to it.
But I apologize for asking a question that possibly is in the draft. But what about pacing limited?
What about?
What if you're pacing limited? You're limited by the pacing rate of the congestion controller, like in BBR, where you can have a C-WIN that's twice BDP, and you can very easily be limited by the pacing rate.
Okay, Gauri, you want to take that? Okay.
So Gauri Fair has seen if I can try and answer this correctly. The idea of rate limited is it's not the C-WIN that's limiting. And we didn't want to say application limited because it's not the application that's limiting. So it includes things that happen lower in the stack and perhaps in a router along the path if that happens. So I think we want to include this, but we really want to get that text right. So please help.
Thank you, Gauri. All right. Any other thoughts? I think one of our questions is kind of, what do we think is left? We've done a nice job of kind of burning down all the remaining questions. What's next?
Just these 2 points. We would just like to relook at the rules, probably simplify them instead of 3 have to, make the second one a must, and just probably define the meaning of the word rate limited in the draft. But I think everything else seems to be done, and we look forward to the feedback from the working group if there's something else that should be added to the document.
Beautiful. So it sounds like kind of, especially if folks can help contribute text to make it maximally clear to them, that'll be super helpful. And then otherwise, same story. This is a great time to take a read through the draft, send feedback, file any last issues before we think we're ready to progress.
Sure.
Lovely. Thank you so much.
Thank you.
Next up, I believe Mark is remote and should be sending us a screen sharing request in a second. There we are. Okay, you should have the ability to pick a window, etc. There we are. All right, and we do not yet have audio from you. All right, we can see you. Wonderful. Can we hear you? I see you have audio enabled on this end, so we think you're sending, but we don't actually hear anything coming in. Nothing yet. We see your mouth moving, but nothing actually coming through. Always exciting. Nothing yet. Do you want me to revoke audio and then you can re-request it? Oh. Still nothing.
Is that better?
So much better.
Oh, okay. It's weird. Sorry about that. Sorry about the technical difficulties, everybody. All right. Should I launch?
Yes, please.
Thanks for being patient with me. Yeah, so hi, I'm Mark Claypool. I've presented here a few times. Those who don't know me, I'm professor at WPI. It's a school outside of Boston, US. This work I've done with Miriam, she's a PhD student of mine, and then Jay and Feng are engineers at Viasat. Yeah, this is going to be a totally different kind of presentation here. I'm going to position sort of search in light of some of the discussion on the mailing list. So not talk with RFC, just kind of talk about sort of where I think it's positioned as an approach, and then talk about some of the framework tests we've been building. So let's see here. So again, slow start. So as we know, TCP slow start roughly doubles the congestion window each round trip time. And so the idea is as you go over time, it doubles until traditionally it passes a capacity point and you get packet loss, and then you enter the congestion avoidance phase. And that we say it's too late. You sort of a missed opportunity of if you can detect it earlier, you can avoid this sort of unnecessary loss. You can sort of operate closer to the capacity point. So that's sort of this green area. You'd like to exit slow start after you've hit the capacity point, before you get to packet loss, sort of that sweet spot there. Approaches that try and do this is like the high start in Linux. And the idea is to detect that you're at capacity before you hit loss. It's the default Linux kernel. And that over many wireless network conditions actually exits too early, detects, thinks it's at capacity point, exits congestion, slow start, enters congestion avoidance. Get sort of this picture where you have underutilization. You're sort of under the capacity for some time. What we're trying to do is again, hit that sweet spot where you double normal slow start rate, you hit the capacity point, but before you get to loss, you detect you're there and then you exit and enter congestion avoidance. So that's the high level motivational view. The way search works is it takes a look at the sent bytes on the top left graph here, and on the sender, you basically 1 RTT later, you can get the bytes delivered, and so that's the delivered bytes, and you can compare those. So at time T2, you can compare, did the bytes that were sent to T1, did they all arrive? And you can compute the difference between those, and there'll be no difference, sort of for the first round trip time, and 1 round trip time later, you can compare the next set, and so on to T4. And now T5, of course, now we've hit capacity. So you sent, in this example, 8A, and yet you only receive 4A because you're at the capacity of the link. And so that difference is above a threshold. So search would say, hey, I'm at the capacity point, you'd exit slow start. The algorithm can do that with just the delivered bytes. So just as the sender sends them out, acknowledgements of delivered bytes comes back. And you basically can go back in RTT in your delivered byte history and say, hey, I expected, I sent, 1 RTT ago, should have had this many bytes sent. So here's what I should have now. And you can basically compare those just with a delivered byte array. And again, at the point where you see this difference, and the difference is you're comparing twice the bytes delivered a previous RTT ago to those delivered now. And you compare that difference to a threshold. You first want to normalize it because you don't really care about the absolute bytes, just the relative amount. So you normalize it by the bytes sent. And if that's greater than the threshold, you exit. So it's a bit of a whirlwind, but I presented this before, and that's the high level description in the RFC draft we have, where this is the high level. The details are about how it works with the binning and the intervals, but this is sort of the basics of the approach. And what I thought I'd do next a little bit is there's some discussion about this on the mailing list. And I thought I'd try and talk about that a little bit. So placing it with other approaches. So how does high start plus plus, what are they like, and how does search compare to those? And I call those sort of delay-based approaches, where they're looking at the delay and the changes in delay to detect the right place to exit slow start. And then the delivered byte-based approach like BBR, and then search. And so just to place it in those. And I have a couple exampple that I'll show you that trying to illustrate where search fits in, and then a bit on the memory use for the delivered byte history part, and then some of the framework we've been working on. Kind of excited about that as a test framework, and it kind of ties in with the opening part of this session, where you need frameworks to sort of test code, and then end with brief summary, but hopefully time for some questions. Okay, so let me do this first part then. So again, we've been looking at geosatellite links with Viasat. And I'll show you some non-geosatellite links also, but they sort of exacerbate the slow start problem in that they're high BDP networks, as we know. And particularly the RTTs are really large. They're 600 millisecond round trip time kind of minimum. And so they sort of exacerbate any problem. The slow start just makes it that much worse. And so let me kind of show you. Here's a typical Viasat link on our test bed, where you sort of ramp up really low bandwidth for a while as you start to get higher. And this is, again, traditional TCP, no high start, nothing, just running. About 10 seconds, rate starts to get noticeable. Maybe capacity around 15. About 20 seconds in, you get loss. So that packet loss, you exit slow start. What's interesting accompanying this is, on the left looks okay. On the right side is the RTTs we're observing. And again, this isn't even scaled from 0, but the minimum RTT is around 600 milliseconds. And you can see they oscillate. They vary a lot over the first 10 seconds. And if you kind of look at the graph on the left, it's not at capacity. I mean, this isn't a congestion signal at all. It's just RTT variation. And it's, going from, it's sort of cyclic, but going from 500 milliseconds to 1500 milliseconds. And then once you, of course, hit 12, 13 seconds, again, the queue starts to fill, and we're getting up to 3.5 seconds on this link. But this is, again, lots of runs will vary and stuff, but this is sort of typical, this RTT variation. So this is sort of what we're dealing with in the link. And then when you take a look at then say how high start is going to work here, again, high start looks at variation change as sort of a spike in the RTT, and it uses that as a signal to exit slow start. So if you take a look at this is a different trace, but here's an RTT signal over the same link. And again, bouncing all around, starts at 600 and goes up and down. And that green dash line here at about 1.5 seconds, that's where high start's going to exit. High start chooses to exit slow start right there. And we're not even 10 seconds in. We're not nearly at capacity. We're just at this RTT variation part, and yet it's going to say, hey, it thinks that's a signal to exit congestion. And sure enough, what it does is it enters congestion avoidance. And we have this really slow ramp up all the way through time 30 in this case before we kind of have hit the capacity of our link. Grossly underutilized, so just really inefficient for the link. It takes a long time to get anywhere. So again, high start just triggers is using that signal to decide slow start should be exiting. It has this problem with the variation in the link causing the problem. And again, particularly bad for high B2B networks. And then high start plus plus to think through that. I know there's some in this audience that like high start plus plus. High start plus plus is kind of funny. It basically recognizes that delay is a tough signal to deal with, that it's noisy. And so it says, well, it doesn't come up with a better signal. It just says delay can be noisy. So let's just cool our jets when we get the signal we're going to leave us. Just hold off, and it enters this sort of conservative slow start phase. It's just kind of trying to be cautious. It says, I don't know if I should exit slow start or not, so I won't. Just go to this conservative stage. Don't grow as quickly, and let's see if things change. And if delay goes down, it goes back to slow start. If it does not go down, it goes to congestion avoidance. And so it's how does that work for, again, things like Viasat? You have this sort of variation going on, and again, it'll exit. The initial potential exit point is kind of the same way early with high start, with high start. So high start plus plus will decide to enter the CSS stage, then doesn't actually go to congestion avoidance. And it, about 5 or so round trip times, it's going to hang out there. And if the RTT comes down, it'll go back to slow start, which it does. About 3 seconds in, it comes down, and it says, oh, okay, cool, back to normal slow start. And it's kind of growing slowly during that first phase. But then it goes up again. And so it decides to do the same thing again. And here it's now about 5-ish or so RTTs, or about time 7. It then says, I'm going to exit the CSS stage, and it enters congestion avoidance. So it may be better than high start in the fact that it didn't exit quite so early. It's like 7 seconds in, but it kind of grew slowly during these CSS phases, and it still exited too early. And, again, high start plus plus is a little bit funny that way. It's slow growth. Means that if high start was wrong, it kind of grew slower when it was wrong. And if high start was right, if it was, let's say that 1.5 seconds was the right point, it's going to overshoot that capacity limit. So in my view, it sort of decided to not be as bad on either end, but it's not really doing a really good job with that signal. And again, here the challenge is this RTT variation is a tough signal to figure out for congestion. And again, the 0 to 10 seconds in this graph, none of these are at capacity. So again, it's just sort of positioning the delay-based approach. Then delivered byte-based BBR, there's some discussion on the mailing list about this a bit. And, the BBR's startup phase isn't designed to be, you can't just plug it in necessarily to TCP, where ours would, search is supposed to do that. But as a contrast, so its approach to exiting startup is, looks at the delivery rate again over rounds, over these RTT rounds. And if any 3 of them have stopped growing by 25%, so 3 in a row, I should say, 3 consecutive rounds, don't grow by 25% if they're under that. And it makes a decision each round. If that happens, then it decides that's the time to exit startup. So if you look at BBR over Viasat link, it sort of looks like this. Here's a trace where 0 to 18 seconds. This x-axis here is the bandwidth estimates by BBR. The vertical lines, those dashed ones, are the rounds where it's going to make a decision on has the bandwidth changed or not. And then where there's a red X, it hasn't changed by 25%. So there's at like 2.5, there's an X. And so at that round, it said, hey, it didn't change by 25%. That's 1 of 3. It's going to do that 3 times before it decides to exit startup. In this case, the next one changes by 25%, so it's not 3 in a row, so it keeps on going. So you can see at about time 11 or so, actually about 60 megabits per second. That's going to kind of flatline there. So this time the link's probably at 60 or so, and you get the first one at 15. So yep, it didn't change. We need 3 of those. And the rounds are getting longer and longer, and they're getting longer and longer because we're filling up the queue. So those rounds are getting longer and longer. In fact, it never gets to 3. It actually hits loss at 18. Because again, these rounds, it sits at that space. And sometimes it's usually at 3 seconds, 4 seconds. You'll sit there for like 12 seconds, even when you don't have loss yet. You'll sit there for about 12 seconds before it exits when it does, or before you get loss. So that's a challenge. As the congestion hits, the rounds get longer and longer, and it has to sit there for 3 in a row. And it takes a long time to decide to exit startup and enter the next phase. So in contrast that to search, which I highlighted a bit. So again, search looks at that normalized difference. And in a nutshell, it's looking for sort of a 30% difference if it hasn't grown by that much. And from the previous RTT, that's sort of its signal. It has a slightly different way of doing that, but that's about the idea. And it can make a decision about every half an RTT. So it can make a decision sooner about to exit or not. And that's because that's the size of these intervals that keeps these bins. And those bins too are not based on the congestion RTT, they're based on the initial RTT. So it's resilient to a queue bloat, where if a queue gets filled up, it's resilient to that because it can make a decision based on the initial RTT. So that this is the same trace. This is that picture of that normalization it picks, where we're looking for, did the difference get higher than some threshold? And the difference of 0 over time means there was no congestion signal. And as it goes up, then it looks like we're not doubling, we're not increasing at the rate we expect. And that happens in this picture at about 13 seconds in. That's a green line where search would decide to exit, slow start there. And then the loss happens here in this picture about 18, so it keeps going. But we exit again before loss. And then capacity point is about 11 seconds, 12 seconds in this run. So it is after capacity. It's kind of right where you'd want to be for this link. Again, this is the same exact trace from the BBR run. So this is the one we just saw. So again, BBR, they both have loss, of course, same state. BBR didn't actually exit startup. Search is kind of hitting it right about after capacity maybe 11 or 12, and it hits it a little bit after that and search exit. So again, it has the ability to sort of exit before kind of waiting for these large queue rounds as a contrast. So, and you might be thinking, oh, this geo satellite link's really quirky. This is maybe a real edge case, but we've seen the same behavior in lots of other wireless networks. Here's just a quick snapshot of like a 4G network where you see some of the same behavior and some of the same contrasts, where again, this is a traditional non-high start cubic run. Probably many of the crowd have seen things like this, but there's the RTT. It starts out low on the left and it ramps up as the queue gets filled and the capacity might change as there's congestion, there's other people on the link, there's other interference. And time 2 is where you actually get your first loss in this run. Throughput ramped up quickly, 150 megabits per second, again, loss at time 2. But again, that you can see that RTT there's lots of variation there. In fact, if you run high start then on this link, here's a high start run. Again, that variation in that initial run, it starts out low, but it kind of goes up, and high start says, boom, there's a congestion signal. Then it exits the slow start phase, goes to congestion avoidance. And then for this run, you can see the throughput just kind of slowly ramps up because it's in congestion avoidance. It takes a while to get up. So some of the same early exit with high start. BBR looks sort of similar, some of the same issues over 4G. We often see it, a little less consistency, but you have these sort of small rounds that get wider and wider as congestion hits because it starts filling up the queue, and it takes a while to make its decision because it has to wait for 3 rounds in a row. And that's sort of, again, this, you can sort of see the capacity at like 1.5, but that green line is where it finally gets 3 in a row and it says, hey, I'm going to exit the startup phase. And that's, before loss in this case, if that's your benchmark for the BBR flow. And search, though, again, can do the same thing, but the idea is because it's looking at this difference and it has a shorter time frame, kind of at a 1.75 or so, and that's about where it's kind of hitting capacity. It makes a decision to exit startup and sort of well before loss in this case. So again, this is a snapshot of another link, and I know these are all just case studies. We've done lots and lots of runs, but I wanted to sort of illustrate what the underlying network is looking like and how the approaches are changing here. So that's kind of a positioning, I think, in terms of some of the discussion of where search fits in and what does it have over other rate-based delivered byte-based approaches, perhaps, or at least BBRs, and then compared to sort of high start plus plus. The other parts of the discussion that we're on the mailing list a little bit is about memory use, because you have this history, you have to keep delivered byte history. So how much memory use is there? And I wanted to talk through BBR and search just a little bit about that. So the memory use for BBR is basically to do the delivered byte computation. For every segment you send out, you need to kind of say when that was sent. And then when the acknowledgement for it comes back, you can do a difference in the time and say how many bytes were delivered. And that's the delivered byte rate. So roughly you have a window size of data, roughly on the order of the CWIN, or outstanding bytes in flight. And then you have whatever the size of the time field is. And that's, broadly speaking, that's kind of the storage needed for that history to do delivered bytes over a window. Search does something sort of different. It basically, at intervals, it checkpoints the sequence numbers that are sent. And it does it for 3.5 RTTs in the past. And so you have this, but it only does this at these discrete intervals. So you have this sort of set of windows that you're doing. And each interval is about half an RTT. And it just, you store the sequence numbers. And then if you want to compute the delivered bytes over a window, then you can just subtract the two sequence numbers and you know the times and you can compute the delivered bytes. So that's its approach that it uses. And if you so how do those compare? Well, it depends. It depends on, again, the size of the CWIN, for example, with BBR at 100 megabit per second link at 100 millisecond RTT. There's about 83 entries or so, roughly 80-ish entries that you need to store, and each of those is a timestamp. Search is fixed. It has a fixed size window. It's based on what we've been testing. We did some derivations of this. The window size is 10, so 10 bins. Then you need a history to roll it back, so 15, so 25. So again, just broadly, it depends on the size of things, but 25 entries. And last time I talked, you can size with different numbers of bits and so on. So maybe less memory, but just again, they're not orders of magnitude different. They're just maybe comparable for that. So what happens, the Linux implementation for BBR has taken that storage, that delayed bytes, the delivered bytes, and it's in a different part besides the BBR module. It's down in the SK buff. So they've done a union of the sort of some clever coding there to optimize the memory. So you don't see it in the module part, but it's needed to do the delivered byte rate. So just to point that out. So again, just it's not like this is using a totally different memory footprint here. So again, that was some discussion on the mailing list on the memory use. Shift gears a bit. The last bit was sort of this test framework. And I'll talk about challenges and kind of what we did. And it was interesting to hear about the test framework part in NS3. That was the opening in opening remarks there. Part of the challenges we've had is as we've developed search, we have different versions of it. We have a version for a quick stack. We're developing a version for FreeBSD. We have a version for Linux, and it's been evolving. Even like BBR has been evolving as you change it. We want to make sure as you add something, you don't break a previous version and all the same kind of regression. And doing that over Viasat links and stuff is just not the way to go. Plus, we want to explore performance tuning so that you change some of the magic numbers, as you will, and how do those work. And so that's a bit of the challenge. And so what we move towards doing, if we took an observation that in order to run things like search, you can do that with a trace. You basically need the arrival time for a packet and the sequence number. And if you have that trace, you can just run that through the code. Now, we didn't want to run that through a simulator, so we actually want to run it through the actual code. So what we've done is we take the kernel code that we built, and you can extract it, and you can then run it in user space. And that's sort of what we built this framework that does that. So you take the code, you extract it into user space, and then you can now it's the same kernel level code, but it's running in user space. We have some support code, and we can actually automatically generate this TCP code that needs to support it. It's like the full TCP stack, but you don't need that whole stuff. You can just populate with dummy variables so it can compile. You can just run the search code as it is. It's just, again, the delivered bytes is what it's making this decision on. It's a few support helper functions that do some of the kernel functions that you sort of hard coded, that sort of baked into the framework. And that dashed box then is something you can basically compile and run. And what that lets us do is you, again, can just work on the Git repo with your code. And when you want to test it, you pull up the framework. And now you can take an input, which is a trace. That's just when the packets arrived and their sequence numbers. And then you can pull those out, and then you can gather those in a variety of places. And those can be input as a CSV into the framework when you run it. And that lets us just, again, vary things and run through a whole bunch of traces and get the same answer. And this helps us to verify, one, if we have a different version, of course, to make sure we're getting the same answer, and to actually compare. I did some tests fail or pass and look at performance. And then the nice thing too is we've actually done this same kind of extraction for BBR startup, so we can run it through the same framework. We've done it for high start, and so that just lets us take traces. This is a way you can do kind of apples to apples comparison. That's sort of what we've been using it for already. So one, to verify and validate the implementations we have. So again, the Linux and the FreeBSD and the quick versions to make sure they're doing the same thing, and the same spec, of course, but they're different code bases. So can we compare them on known input to known output and get the same answers? And then we can compare performance across things. So for example, if we take a trace, you can run the same trace through sort of traditional TCP, TCP with high start, TCP with search. And it's an apples to apples comparison because it's the same. You can run the code 3 different times. It's not a repeat. It's deterministic, and you can compare them like this, where like the green line is where search would exit in this run. The blue line is where high start would exit. The red line is where traditional TCP would exit. You can do this over as many traces and keep them around and run them. You actually, to some degree, can compare, and we've done this, as I showed you in this talk even, but comparing search to BBR, where you can take a BBR trace and those packet arrivals, you can run them through a search module and vice versa. There's some slight differences, of course, because BBR is paste and it would not be for search. But in the aggregate, we've done a bunch of these work almost the same. And you definitely get the algorithms output on that input. And so you can kind of compare those as a head-to-head fashion. And we've been doing some of that too. It's not a main goal, but it's sort of a side benefit that lets us compare those. And we can do that with high start plus. So that's the framework we're building. And I think it's really useful for this kind of testing for this startup where the algorithm is just determining based on the arrival of packets, because you could just run the trace through it and yet use the kernel level code, which will let us compare versions of it. So we're in the process of gathering a whole bunch more traces to do this with sort of the normal cases, but then all the edge cases, like where it's rate limited or window limited or something else happens, or you get some sort of interruption. There's lots of edge cases to make sure your code does what you want it to. And then again, lots of wireless environments, but in addition to wired environments, so we'll have hopefully a large set of traces that we can just run through, and they all run really fast because it's you can crank them through the user space. It's not like you have to do real time for these. You're not really transferring the data. So yeah, I'd be happy to chat about this a little bit more. It seems like this kind of thing would be great to have as a tool for others that do this kind of work to enable them to develop and test. And we're already making use of it, but I was happy to share a bit on this. Yeah, that's summary. So again, that's search. Happy to talk about it more with questions. I think it's designed to hit the choke point, we call it, but after capacity before loss. We have this framework that we've sort of been developing. I told you a little bit about that. And again, looking for people that want to try and deploy it. Real world deployments would be great. Either our implementations, happy to deploy them, or talk through or help build somebody else's for implementation. And that's it. Happy to answer any questions. If you want to contact any of those, you can ask me now or send me an email. It's pretty easy. And Jay and Fung, I think, are here on the call too, so they could perhaps take some questions.
Thank you, Mark. All right, we got some folks in the queue. Please do keep in mind we only have a couple of minutes left, so let's keep it snappy.
I'll try. Mia Kulevin, first of all, thank you for looking and comparing to the other algorithms. I have 2 points. One is if you look at mobile networks and you actually start your simulations on an empty link, there is an off by one error in the Linux implementation of high start, which causes this problem. So it's actually not part of the high start algorithm. It's like they actually implemented it wrongly, or like never implemented it right, I guess. So I can send you a paper about that. So maybe try to, and I don't think this fix is applied because we mentioned that to the Linux developers, and they told us, yeah, we can put it into the kernel code, but you have to test all these things. And we're like, we don't have time to do the tests. So I don't think it's in the code. And it only applies to mobile links if you start on an empty link, because on those connections, the first packet of each round trip time get piggybacked to signaling traffic, and so there's a lower round trip time, which is really confusing for the algorithm. So double check that one. But the more important point is, yes, you looked at performance, and like if you look at these specific scenarios where high start has problems, I see that you have an improvement, which is great. But what I would be more interested in to look actually at the algorithmic differences, because you're still using a delay bait algorithm, but you put it in a way that you say this is like this completely new thing, which is great. But I don't think it is actually that new. I think there are similarities to high start. I think one of the main improvements you did is that you filter your delay values over a longer time. And that kind of causes you to not exit that early, which is also something Christian just mentioned in the chat, that he had observed a similar problem and he had filtering and he could solve that problem. And the reason why I'm saying this is because if we would understand what are the differences are to high start, what are the main impacts that actually make this improvement, I think it would be much easier for us to evaluate these algorithms rather than having like this really complex new thing that we don't have a lot of deployment experience with. So that's what I would like to understand. What are the algorithmic differences?
Yeah, thank you, Mirja. I'll just take that as a comment and happy to have other comments. And thank you. You shared that on the mailing list as well. So, and I responded then. I'd be happy to do that now, but maybe we could go on to another question if somebody else wants to ask. Thank you for that.
Yeah, so nice presentation. Thanks for the presentation. One thought I had was that I think you mentioned something about the buckets being timed to the minimum round trip time or the initial round trip time.
Yes.
I'm curious if you have played around with this on Wi-Fi links. Have you experimented with that?
Yes, we have.
Okay, because one thing we've seen with Wi-Fi links is that it seems like the RTT variation can be quite extreme. So, for example, we had some slides at IETF 101 where we showed an example where the min RTT measured was 4 milliseconds, but RTTs go as high as 80 milliseconds. So there can be like a 20x variation in the RTTs, and I'm a little concerned that if the algorithm is sort of using the initial RTT as the time window that is the basis for the bucket length, it might be sort of missing out on the packet dynamics, which might be happening on a time scale that's much longer than that initial RTT. So I'm wondering if it might make sense to sort of keep track of the buckets on the time scale of the recently measured RTTs so that it's sort of more closely corresponding to the current dynamics. I don't know. It's just a thought, but thank you very much.
Yeah, no, it's a cool thought, Neil. We have search has been less successful over Wi-Fi, and maybe that's some of your insights might be some of that. So thanks for that tip. We'll keep that in mind. Thank you.
Altanaisis Komiraki. The paper was very nice. Thank you for explaining. I have a question specifically around asymmetric networks. I know some of algorithms are more sensitive than others. Some employ gradients and are less sensitive. How would you rank this approach in asymmetric networks?
I'm sorry, I don't understand the question. Are you saying asymmetric networks?
Yes, asymmetric networks where one of the links is more performant than the others.
Yeah, that's a good question. Offhand, I don't see that would pose a challenge, but maybe I'm missing something. Do you have some insights into what might be a challenge there?
Yeah, sure. So if one of the, let's say the downlink is more performant than the uplink, then only one path has more performance. The other path suffers with buffer bloat or ACK compression, and basically the measurements that you obtain then on one end are wrong, or rather not wrong, have errors in them. So you don't get the full picture.
Yeah. So you're saying if the congestion, if the bottleneck is say on the uplink for the ACKs coming back from the download, is that what you're saying? If that's the bottleneck.
Correct.
I don't have a quick answer to that. So thank you for that. That's a scenario I guess I haven't thought through. I don't immediately see that search wouldn't work there, or at least comparatively to others, I don't immediately see that, but I might be missing something. So thank you for that tip. We will think through that, and I don't have a quick answer to you. Thanks.
Yeah, I can actually answer that question a bit.
Before we go into that, since we're slightly over time, this would be a good conversation to chat about offline, and then whatever comes out of it, let's bring that back to the group.
Yeah, thank you.
Thank you for jumping in. Christian, last comment.
Yeah, I mean, thank you, Mark, for the presentation. That's very good to show all these problems that basically we cannot trust delays. We cannot really trust bandwidth either, because bandwidth is measured by dividing packet received by delays, so it also has some jitter. but we can try to be better, and trying to be better is good. Now, my main problem there is what you outline, is that try hard as we can, we are going to make mistake during the first phase of the connection. And the reason it's a problem is because we have designed congestion control protocol for more than 40 years. Well, no, not quite 40 years. With this idea that we have a first phase in which we try really hard, and we have a second phase in which we try really, really slowly. It was not quite as slow 30 years ago because the network was relatively slow, but now it is. That means that if we make a mistake in the first phase, we are going to pay for it for a very long time in the next phase. And I think the theoretical response there is that we should not have that much difference between the first phase and the second phase. And that we have that much difference is what caused that. Now, that is a rejoinder to the discussion we had about cubic compatibility with cubic. I mean, the second phase of cubic is kind of faster than the second phase of Rhino, but it's still really, really slow. And so if we try to be compatible with them, we inherit their bug. And we are stuck with this problem of if we mess up in the first phase, then we are stuck for a very long time after that. And we have to get out of this thing, and we have to be able to try harder sooner. That's pretty much my conclusion from your presentation.
Yeah, no, thank you for that. And I think your email had a similar comment about not being saddled with a poor choice that wrecks your whole phase because you made a bad choice in the first phase. So that's a nice insight. Thank you.
Wonderful. Thank you very much, Mark. And I believe that concludes our session for today and at this IETF. Thank you, Martin, for taking such diligent notes. And we will see you all on the list.